Okay, so let's get started. So I'll just do a quick recap. Last time we did some introductions to operating system structures and so on. So we'll continue from that point on. What I'll do today is basically a refresher of computer architecture. If you already taken a class on architecture, this is probably going to be very mundane and boring, but I think for you may have forgotten, you may not have taken, some of you at least may not have taken a course. So I think it's important to understand the basics of computer architecture, because OS is the piece of software that interacts most closely with the hardware. So you need to know something about hardware concepts for you to understand how an operating system manages that hardware. Okay, so we'll spend much of the time talking about architecture today, and then starting next class we'll start with microkernels, which is the first real topic. Okay. So before I start, just some logistics. I already announced my office hours, which are Thursday before class. I will at some point add a second slot as well on Tuesdays, okay, very soon. The TA is available Wednesdays and Fridays from 4 to 5 in the LGRT, the tower. Don't need to write this down. I'm going to post this on the course web page and also Piazza, so it will be easy to find. But I just want you to know that Tuesday, Wednesday, Thursday, Friday, there will be someone available every day, okay, except for Mondays. Okay, and of course, if you post to Piazza, will be there on other days as well. All right. So the other thing is every class I'll need a volunteer to take notes and then make that set of notes available to the rest of the class. I think we kind of skipped lecture 1, but for today, is there somebody who wants to volunteer, take some notes? Okay, so you're going to take notes. Send me a note after the class so I know who you are. Okay, and then the other thing I will do is I'll send around a sign up sheet. So if you feel like volunteering, you can just put your name down, and then we'll send you a reminder the week before saying you signed up for this class. Make sure you come to class, take notes and whatnot. Okay, all right. So as I said, today is going to be computer architecture basics. We'll start with the refresher. We'll talk a little bit about OS concepts, and then also try to understand how hardware features actually enable those concepts. So it's not like a full-fledged or full-blown refresher of computer architecture. We'll focus specifically on those hardware features that are most useful to an operating system, try to understand what those are. And then subsequently, as we start talking about scheduling and memory management, we'll encounter these concepts again, and then you'll understand how the software makes use of these hardware features. Okay. So here is a picture of what a computer looks from the inside. Okay. So if you actually have a desktop computer, you open it up, that's what it's going to look like. There's a schematic and there's a photograph. They're kind of the same. Okay. Basically, you will see that there is essentially a processor. There are some slots where you can add new devices, peripherals. There are some slots for memory, which are shown in blue there. There are all kinds of ports like USB ports and so on and so forth. Okay, so if you have opened a machine, you built your own gaming computer, you know some of this. Even if you haven't, you can actually now get these tiny computers, which this is a Raspberry Pi. Right, so it looks exactly like that, except that it's much smaller. Right, so so this is essentially what's called a single board computer. It has essentially all of those features. There's a processor here, there's a RAM. You'll see that there are USB ports and Ethernet, and there are all kinds of pins that allow you to add additional peripherals to it and so on. Okay, so that's basically what your PC looks like on the inside. At the bottom right there, okay, which is basically this picture here, you see what a laptop looks like. Okay, that's when you open up a laptop. Much of the space is taken up by a battery. Okay, so what is actually at the top here is essentially all of that, and then all these black boxes are essentially batteries, because it needs a big battery to sustain itself. But other than the battery, everything else is essentially the same. Okay. So let's take that picture and now try to simplify it a little bit. Okay, so if you say what are the key components of whatever was shown on that picture, you'll see it on this slide here. Okay. So there are 4 or so key components. There is a processor. Every machine needs to have a CPU. Okay, it may have multiple cores, it may have one core, that doesn't matter, but there is a processor, that's the component that's going to execute your programs. Okay, that's the CPU. Okay, there's memory. Okay, that's where your programs are going to reside when they execute. Okay, there's going to be at least one storage device, a disk of some sort, which is where all your files going to live. Okay, you might have some network subsystems or other peripherals that are shown, like a graphics adapter and things like that. Okay, and then what's at the center is the system bus. Okay, so that's essentially the interconnect that allows these components to communicate with one another. Okay, that's the piece of hardware that enables this communication. It's a high-speed interconnect. Okay, so that's the picture to keep in mind. Okay, now we'll look at some of this in a little more detail. Okay, is this clear? Any questions on this? Okay, it's very basic stuff at this point. Okay. So now let's step back and say, what does an operating system give us? And then we'll ask, to enable that functionality, what do we need from the hardware? What hardware features do we need? Okay. So here's a set of features that you expect any general purpose operating system to provide you. Process management. It needs to manage applications that are running. Okay, you need to essentially do process and thread management. You might need to do concurrency if your applications are threaded. Okay, you need to provide concurrency support. Okay, you need to essentially manage all your I/O devices, whether it's disks, whether anything you plug into an USB port or the graphics card. All of these are I/O devices from the perspective of the OS. It needs to manage all of those. Okay, it of course needs to manage memory. Okay, decide where processes fit in RAM, how much RAM to give each process, and so on. Okay, it needs to manage files. It's basically essentially manage files on your disk, and then if you are looking at multiple machines that communicate with one another, you need to manage the network card, which enables you to communicate. Okay, so you can have a browser, talk to a web server, and things of that sort. Okay, so those are by and large, at a very high level, the functionality you expect from an operating system. Okay. Now let's ask, to enable all of this, what do we need from the hardware? Okay. Now there are a number of things here. We are going to go through them one at a time. Right? So the first service is essentially called protection. Okay, we have multiple processes running. You want to ensure that one process does not go override the memory of another process. It doesn't do bad things. Okay, so you need something called protection. You don't want a process to go override the operating system kernel or any other process memory and so on. Okay, so the first service is protection. Okay, and we'll look at the hardware features that you need to support it, are user mode and kernel mode bits, protected instruction based limit registers. Those we are going to see in a moment. Okay, so okay, the second feature is interrupts, and we'll see why you need interrupts. Okay, and then you essentially have hardware level interrupts to support interrupts in the OS. Okay, we'll see that the OS provides an interface to all applications. Okay, so that the OS interface is called system calls. Okay, any application which needs to communicate with an OS needs to essentially use a system call. Okay, so to enable system calls, we have trap instructions and trap vectors. Those are the hardware features that you are essentially using to support system calls. To do I/O, we need interrupts, as we'll see in just a moment. If you want to do things like scheduling and accounting, okay, scheduling is the problem of deciding when a process gets to actually execute on the CPU if there are multiple processes. Okay, so to do that, you essentially need a timer instruction which tells you how long each process gets to run. Okay, a synchronization, if you are essentially done things like locks and semaphores and whatnot, you essentially need hardware level support to enable it. Okay, there are specific assembly instructions that essentially allow you to implement things like locks, which are called atomic instructions. We'll see those also later today. And last but not least, if you want to provide a virtual memory abstraction where the memory that is seen by applications is not limited by the amount of RAM you have on the machine. Okay, as far as applications go, it looks like memory is infinite. Okay, not really infinite, but looks like it's infinite memory. So it is using a virtual memory abstraction. Translation look aside buffers or TLBs. Okay. So those are all the hardware features we want to look at in the rest of the class. Okay. But it should be clear why we are talking about those specific features, because there is at least some OS functionality that directly needs them. Is that clear? Okay. So, I am going to pause here to ask if there are any questions before we start talking about each of these. All right. So, let us talk about, so we basically did the first small piece of the lecture. So, we are now going to move on to the next piece where we are going to look at these features. We will start with protection. Okay. What is it and what does it mean? Okay. So, here on this slide you see some assembly instructions. Maybe only slide you have in the course that might have assembly instructions. Okay. You don't need to understand most of them, but by and large, what do? They allow you to move things in memory, they allow you to do arithmetic computation. You will see that there is a halt instruction, okay, that essentially halts the machine. There are things that do load and register, there is an instruction that allows you to do interrupts and so on. So, assembly instructions are essentially the language that the CPU speaks. Okay. So, those are the instructions that actually executes on the processor. Okay. And there are each depending on the CPU, whether it is a x86 an Intel CPU, whether it is an ARM CPU or some other kind of processor, it will have its own set of assembly instructions, which are the instructions that that processor understands. Okay. Now, if you look at the instructions that are supported by the processor, you will see that there are some things that look like they are more sensitive than others. Okay. So, on this slide you will see, let us look at the halt instruction. Okay. That is essentially going to stop the machines, powering it down. Okay. So, now if I say, should any application process be allowed to execute halt? Okay. Seems like you shouldn't, because you can just write the program, say halt, you run it and the machine just shuts down. Okay. That is not what you expect an application process to do. But if it wants to add 2 values in a register, fine, those are all instructions that just seem like they should be allowed to execute. Okay. So, what this is saying is, there are some set of instructions on it that are part of the CPU instruction set that are essentially going to be sensitive. We do not trust application processes or user processes to actually execute them. Okay. We only want some trusted piece of software, which in this case is the OS, is the only one that is going to execute. I mean, there are others that we will let any application or any process execute. Okay. So, there you have now these 2 sets of instructions, one that any process can execute, and then another one which we only expect the OS to execute. Of course, OS can execute the other set also, because OS can do whatever it wants. It is the piece of software that we trust. Right. Now, the question is, how are we going to enable this functionality? How do we ensure that only the OS can actually execute something and not user processes? Okay. That is how protection is going to come in. That is the feature that the processor provides us to enable protection. Okay. There are many ways to do this, okay, but I am going to start with a very simple method. Okay. So, we are going to essentially have one bit on the CPU. Okay. It is called a protection bit. Okay. If that bit is turned on, okay, then what we are going to say is that you can execute any instruction on the CPU. Okay. If the bit is turned off, you say that you are not allowed to execute the sensitive instructions. Okay. So, depending on the value of this bit, okay, you are going to be either in what is called user mode or kernel mode. Okay. So, as the name suggests, user mode says that a user process is actually running on the CPU, and only the more limited set of instructions are allowed to be executed. So, in user mode, if you try to execute halt, you are going to get an error, so you cannot do that. Okay. But then if you are in kernel mode, then anything goes, you can execute any instruction, and the assumption is the kernel mode should be set only when the OS kernel is executing, not when a user process is executing. Okay. So, whenever the kernel executes, you flip that bit, go to kernel mode, so the OS can do whatever it wants. Whenever a user process is running, you flip it back, so that you can only execute the more limited set of instructions. Okay. This is going to give us very simple protection using a single bit. Okay. Every processor actually has to support this, otherwise you have no protection. Any process can do whatever it wants and execute any instruction, and then you can go and access any process's memory and so on and so forth. Okay. So, the slide also lists what are some of the more such. I explained halt as one of those instructions that a process should not execute. Okay, but that's not the only one. That's a trivial example. The slide here actually shows you other things. Okay, so for example, I/O is sensitive. Okay, you do not let processes directly do I/O. Okay, you expect the kernel OS to do it for you. Okay, memory management is also sensitive. You don't want processes to again go access memory belonging to other process, decide how much memory is allocated to a process. All that's done by the kernel. Okay, changing of the bit itself has to be sensitive. Okay, if a process can flip the bit, then it can just flip it and do whatever it wants while it's executing. So that has to be sensitive as well. Okay, enabling and disabling interrupts has to be sensitive. Okay, and then halt, things like halt is also sensitive. There are many more, but that's by that's a good representative set of what we want only the kernel to do and not a user process to do. Okay, so the simplest approach is two modes: user mode or kernel mode. Okay. Now you can of course do more than that. Okay, that's what that picture shows. You might say, what is that circle with all those rings in color? So that's essentially how an Intel processor actually implements this idea. Okay. So in x86 processors there are more than two modes. Okay. In this case you see there are actually four modes. Okay. There's the kernel mode, that's the where anything is allowed, and then there's a user mode where very limited things are allowed, but there are modes in between where you allow more and more things to be executed. Okay. So essentially this is implemented in x86 using the concept of what is called a ring. Ring 0 is essentially equal to kernel mode. Okay, it's a logical abstraction. There's no real ring in the process. Okay, it just means that you are in kernel mode. Okay, if you are executing in ring 3 or level 3, that means you are in user mode. That's the most restrictive. You can only run user processes there. Okay, but you will see that now there are ring 1 and ring 2 where you can do less than the kernel but more than a user process. Okay, is that clear? What I just said. Okay. So now those rings that in between user mode and kernel mode is where we can do more interesting things. Okay, last time I was talking about micro, you remember. We said we can run all these OS services in user space. Okay, so we can run file systems, memory manager, and said how can you do that if it's at the if they're all the same as any other user process. What we are actually going to do is not treat them as a real user process. We are going to run them in intermediate rings, so they are actually a little more privileged than a normal user process. Okay. So you can also have things like device drivers running in ring 1 or ring 2 where they are less privileged than the kernel itself. Okay, so you can actually make use of multiple levels of protection, not just user and kernel mode. That's the x86 mode. Okay, every CPU is going to at least have this bit where you have two modes, but some processors may have more than two. Is this clear? Any questions on this? Okay. Okay, those are protection rings. Now we can ask, okay, so you can't actually do certain things in user mode, but what if a process needs to do something that requires it to access some of these sensitive instructions? Okay. In particular, we'll take one example from the previous slide, which is I/O. Okay, I said there, if you look at the slide, it says I/O is privileged. Okay. Now, what does that mean? It means that only the OS can actually read or write to devices. Okay. Now, you might say that is that true? You've written programs that read files, right? So you can read files from user mode. And I'm saying that you can't do that because it's a privileged operation. So how is that going to work? Of course, you want user processes to be able to read and write files, okay, to do their work. Okay, but they're not going to actually do it themselves. They're actually going to ask the OS to do it for them. Okay, that's essentially what's going to happen. Whenever you have to do file I/O, you are going to execute some call that's actually going to request the OS to do it for you. Okay, because that's a privileged operation. You can't let an process actually go and really write to some random location on disk, then I can override whatever is on that disk. Okay, so you want the OS to check, are you even allowed to access this file? Do you have permissions to do that? Okay, and all of those other things have to happen before you are actually going to do I/O. You can't trust user processes to do that. Okay, so you are going to actually, when you do file I/O, you are going to ask the OS to do it for you. Yes, question.
Are there ever specialized systems where if efficiency is really important or something like that, you might essentially
Yes, the question is, can you have specialized systems where everything essentially runs as a single kernel? There are, of course, systems like that where you are not going to run any user programs, only one program. This is a single purpose machine. Okay, you have anything that's a microcontroller, like things that you have in a car or other things like that, they are going to not run arbitrary programs. This is one program. You trust that program is basically, there's no distinction between an OS and a process in that case. Everything runs in one mode and that's all you do. But by and large, that's not how things are going to work. Even your phone is going to have this feature. You're not going to download an app and let it do whatever it wants, for example. Okay, so the number of systems where you have this very special purpose needs are very small. They're mostly embedded systems. Anything that's general purpose, laptops, phones, servers, they basically have to do this. Okay, all right. So now let's ask, how are we going to do file I/O? Okay, so the way we do this is essentially we need a way for an application process to invoke an OS function and say, go do this for me. In this case, you are going to say, go read some data from a file or write some data to a file. Okay? And so that's going to basically require us to implement a functionality which is called a system call. Okay? The system call is essentially the set of functions that the OS exposes to application processes. It is the API that your OS actually provides. Okay, we don't call it an API, we call it a system call. Okay, but that's essentially what that is. Okay, every OS is going to have a list of system calls it supports, and I'm going to show you several in just a moment, and you're going to write one very soon. Okay, once you get into the labs and whatnot. Okay, but coming back to how system calls work, there's a picture here which shows us how this is going to work. So let's say your application process, it's running maybe Python code that you wrote, it needs to now write to a file. You want to write some string to a file, you're essentially going to call your Python function to do that I/O. That Python function, when it tries to actually execute that function, okay, is essentially going to cause what is called a trap that essentially causes the OS to start executing. Okay, the OS is then actually going to take your request and execute it for you. Okay, and then the results are going to send back to the application process. So the timeline is actually shown here. Okay, so here the x-axis, which is not really shown, is time. So user process executing, you call a system call that invokes what is called a trap. The trap is essentially a software interrupt. Okay, whenever you have a trap, you have a software interrupt that's going to essentially invoke the kernel. It's also going to change the mode from user mode to kernel mode. Okay. At that point, OS is going to take over. The process is going to be suspended. The OS starts executing. Okay. Now it's in kernel mode, so it's actually going to go and execute that code for the system call, which in this case is file I/O. Okay, you're trying to write something to a file. You're going to do all of that. Okay, and then once you have the I/O done, you essentially flip the mode bit back and you hand back control back to the process. Okay, the process now sees the result of your I/O, which says, okay, it worked, and then you continue execution. Okay, so now you see that you actually need to have a trap. Okay, in this case, the trap allows you to switch from executing a user process to executing the OS. Okay, trap also allows you to flip the bit from user mode to kernel mode and then flip it back to user mode once you're done. Okay, this is where all this hardware functionality is going to come in. Okay, and of course, the actual execution of I/O instructions, which are all the assembly instructions that allow you to do I/O, all of that is actually being executed in the kernel, not in the user process. Okay, so it looks like our process actually did I/O, but it's really the OS that did it for that process. And the same thing is going to be true for any other system call as well. There are many, many system calls, as we'll see on the next. Any questions on this? Okay. So now let's just take a look at some. So here is a list of system calls that you see in any Unix like Linux kind of type operating system. We are going to come back to system calls as an entire lecture, so I'm not going to spend much time on this, but you will see that for things like creating a new process, terminating processes, for doing all kinds of I/O, there are system calls. There's lots of system calls for doing memory management also, which are actually not shown on this slide. Okay, so what this should tell you is this is not something that's uncommon. This actually happens fairly frequently when you execute any process, because lots of things that the process does actually involves asking the OS to do it for you, I/O being the most common thing. Okay. Now there are, so that's Linux, and then if you see Windows, you will have a similar list. The names are different, but they by and large do the same thing. You'll see things to create processes, terminate processes, open a file, read a file, write to a file. All of these are essentially system calls. Okay. Does this make sense? Yes.
So, 2 slides back there was a point that architecture must let OS verify caller parameters.
Yes. So we didn't actually talk about how system calls work entirely. Okay, I've glossed over some details we'll get to when we do system calls in more detail. So the question that is being asked is essentially how are you going to verify parameter? Okay, so what is a system call? It's a function. Okay, any function has arguments. You're going to pass arguments. Okay, if you're simply calling a function within a process, just put that arguments on a stack, then you go execute the function and it picks those arguments from the stack. That's how any function executes. Okay. Now, the system call is a special kind of a function. Okay. When you call a system call, you are essentially going to start executing a kernel, which is a completely different process. Okay. So, simply putting your arguments on your process stack and then starting to execute a OS kernel is not going to really work in terms of passing arguments. You need different method to do that. Okay, because OS is a different process. You are looking at a stack of another process. So how do you pass parameters in a system call is going to be somewhat different, and how you pass parameters in a normal function call invocation. Okay, and we'll get to how to do that. Okay, we don't need to worry about this. Is more architecture. We're not talking about how to implement system calls yet. Okay, but there are lots of subtleties to think about, which here we can gloss over. Other questions? Okay. So now let's talk about other types of protection features that we have in the on hardware to enable. I don't know what happened here. Okay. So there are other kinds of OS features that are also involved in providing protection. One is memory protection. Okay. So what this does is it prevents any process from accessing memory that is allocated to some other process. Okay. You can only access your own memory, not memory that belongs to the OS or some other process. Okay. That's important, because if you let any process access any part of RAM, then you essentially can go and read something sensitive that some other process has been doing. Okay, your browser may have logged into your bank. Some random process shouldn't go and try to read what is being shown in your browser in terms of your money in your bank account and things of that sort. Okay, so these kinds of things are not allowed, and the OS essentially has hardware features that allows you to provide this protection. Okay. Again, the simplest way to do this is to use two registers, okay, called base and limit registers. That's basically what is shown there. So in this picture, you will see that there's an OS, okay, that's been loaded, and there are some processes 1, 2, 3, 4 that are loaded. Okay. Here they're shown contiguous. That's not how actually memory is laid out, but for the purpose of this class, let's assume that they're laid out contiguously in RAM. Okay, although that's not really how it works. Okay. So you will see that the process 2 essentially starts at that location and it ends at that other location. So it has a start address in RAM and an end address in RAM. Okay. So your base and limit registers are going to hold the start and the end address, and whenever this process executes any instruction that accesses a piece of memory, whether it's in the stack, whether it's in the heap, anything you allocated in memory, you are going to check the address, okay, and see that it lies within the base and the limit. Okay. That means that it's a valid address. If you try to basically access some other address, you are going to be denied, because that range check which is performed in hardware is going to fail. Okay. Very simple method. There are many more sophisticated pieces of hardware that you will use when you have things like paging and segmentation, but they all do range checks essentially. Okay. So anytime you have a memory instruction, in this case actually an assembly instruction, you are going to actually perform this range check. Okay. It should be clear why this has to be done in hardware. Okay. That's for efficiency reason. Okay. every time you access memory, if you are going to actually do a range check, which means execute 10 more instructions to check whether you are within those values, you are going to slow down your machine tremendously. Okay, because memory accesses are frequent. So, you want to essentially do this in hardware by loading two values into a register and essentially doing that comparison in hardware, which means it is going to be fast, it is going to be done as part of executing that instruction. Is that clear? Okay. So, that is essentially memory protection, and then if the protection fails, you are essentially going to create have a trap, which is some called segmentation fault, and terminate that process. Yes, question.
I mean, how can we, like, we have to have two registers for each program, for each process, right? So, like, how do we already define the I mean, how can we define the number of registers before we know how many processes we can have?
Okay, the question is, you need two registers for a process. If there are many processes running, how many registers will you need? Okay, you only need two registers because there is one CPU and you can only execute one program at a time. Okay, so, the same register gets reused for some other process. So, when you start executing the process, you are going to do some bookkeeping, you are going to essentially load the base and limit registers before you start letting that process execute. Okay. Once that process execution or that quantum that you give to a process finishes, you are going to save those values, load the next register and so on. So, you only have two in this case, not more than two, even though every process needs two. Okay. Any other questions? All right. So, this is the picture you will need to keep in mind by and large when we talk about processes. Okay. Typical process which is laid out in memory is going to have segments. Okay. Segments are basically pieces of that process. Each segment has a purpose. Okay. So, you have what is called the text segment is essentially where your code resides. That is what the code you write when it gets translated into assembly or machine code essentially becomes part of the text segment. Okay. And there are two other segments at a minimum that are important and part of every process, which is the stack and the heap. Okay. Heap is dynamically allocated memory, okay, and stack is something that you use for static allocation. When you invoke a function, you push things onto the stack and things of that sort. Okay. Local variables of a function are part of the stack, but whenever you dynamically allocate memory using new or malloc or it may be automatically done for you in case of Python and things of that sort, all of that goes on the heap. Okay. So, you will see that in this case the data segment is actually the heap. Okay. It is also called the data segment. So, you have the stack, the stack at the top, it grows downwards and then the heap is actually going to grow upwards. Okay. You do not want them to overlap, in which case they will trample one another, but these segments are large enough that you will not have that problem. Okay. So, that is the canonical picture of what a process looks like when it is laid out in RAM. In reality, the process does not look anything like that, okay, because not stored contiguously at all in RAM. It is going to be spread across all parts of RAM because you are going to essentially use things like paging. But that is the logical view of a process. Okay. So, the logical view looks nice because it has a start address and an end address. We are going to put that in our base and limit registers and everything works nicely. Okay, but there are lots of details underneath that you have to take care of. Yes.
So in that case, since it's not contiguous, how do we avoid the overlap of the stack and heap?
Okay. So, if it is not contiguous, how do you allow for this overlap? So, for the purpose of execution of the process, it looks like it is contiguous. The process does not know that it is not laid out contiguously in RAM. It just looks exactly like this when it is executing. Okay. There is some additional logic which allows us to take parts of this process and put it wherever we want it in RAM, and all of that translation is done transparently by hardware and the OS in some cases. So, you do not actually see this when you are executing. When you are executing, this is what the process thinks it looks like. Okay. But underneath, that is not how it is actually laid out in memory. So, it is transparent to the process is the short answer. It does not need to worry about it. Other questions here? Okay. So, three segments to keep in mind. Okay, now, let us talk a little bit about hardware features like registers and so on. So, you should all know what a register is. Right. So, this is essentially the fastest piece of memory you have on your machine. That is where you are going to keep things like frequently accessed variables and so on. Okay, those are called general purpose registers, which any process can use to store any frequently accessed variable Okay. And there are some special purpose registers. Okay. There are at least 3 that you should know of. Okay. One is the program counter. Okay. That is a register that has an address that points to the next instruction that you want to execute, or the current instruction if you are executing that instruction. Okay. So, the program counter essentially points to whatever you are executing, and it is going to execute the code sequentially until you have function calls or loops or things of that sort, in which case it will jump to wherever you need to jump. Okay. That is the program counter. And then you also have the stack pointer and the frame pointer, which essentially points to the beginning of the stack and things of that sort. Okay. So, those are at least 3 special registers. We of course saw base and limit register, those are not listed here. Okay. Those are also special purpose registers. Okay. So, you will have general purpose and special purpose registers. Okay. Whenever a process starts execution, it is the job of the OS to load all the special purpose registers from wherever that process left off last time. So, it will reload the stack pointer. So, it points to wherever you stopped the previous time the process executed on the CPU. You will reload the base and the limit registers. You will again reload the stack pointer to where the stack is, and so on and so forth. Okay. So, the OS has to do some bookkeeping in this case, okay, in terms of managing registers and so on. Okay. So, let us talk about the memory hierarchy. Yes, so you have registers that are the fastest pieces of memory you actually have on your machine. Okay, and then you have caches that your processors support. You might have something called the L1 cache and L2 cache and L3 cache, that stands for level 1, level 2, level 3. Okay, the levels actually dictate how large the cache is and how fast the cache is. Okay, caches are all optimization. A cache is a fast piece of memory where you are going to store frequently accessed data or code, so that you do not actually have to fetch it from memory, which is slower than the cache. Okay, so, that is by and large what a cache means. So, typically on hardware you are going to have multiple levels of caches. Okay, so in this case you have RAM and 2 levels of cache, L1 and L2. In some processors you might have L1, L2 and L3. That does not really matter how many levels you have. What matters is that the caches are actually being used as a performance optimization to speed up the execution of the program, because if everything has to be fetched from RAM, it is going to slow you down. Okay, because you will see that in this case the speeds are also shown. I guess the RAM speed is not shown yet. Okay. So, RAM in this case has 100 cycle latency. It costs 100 cycles, okay, to access RAM. Okay. When registers are 1 cycle, so 100 times faster. Okay. So, you will see that caches might have 2 to 7 cycles. So, they are significantly faster than RAM. So, if the code or data that you are going to execute next, okay, is already in your cache, is going to speed up your execution. If you have to go to RAM, then it is going to slow you down. So, you want to use those caches well. Okay, the only thing is that processes have neither the process nor the OS has any control over caches. All caches are managed by hardware. Okay. So, the OS does not actually have any real control over what is going on the cache. It is all being done by the CPU when it is executing instructions and data, it is just putting things in the cache in the hope that you will use it again, because you will have correlations in how you access data, how you access code, because you might have loops that repeatedly access the same thing over and over again, things of that sort. Okay. And then in the memory hierarchy at the bottom you actually have disk, which you will see is substantially slower, orders of magnitude slower than RAM. And then of course, you can even think of network as being yet another level of the memory hierarchy. If the data you are accessing is not even stored on your disk, it is stored on some remote machine somewhere, and that is going to be even slower in some sense. Okay. So, that is your typical memory. That we will talk about most as far as the course is concerned is RAM and to some degree registers, but the role of caching should not be underestimated. It can actually get quite complicated in how cache management works, especially when you have multiple processors and things of that sort. Okay, so, I have already mentioned L1, L2, L3, so I will just ignore this for a moment, but show you how that picture changes when you have multiple processors on multiple cores. A core is, for the purpose of this class, very similar to a processor. Okay. Everything is multi-core, even your phone has at least 2 to 4 cores these days. Okay. So, no longer are most systems uniprocessor, they are going to be multiprocessor. So, in a multiprocessor world, this is how you should think about how the system is laid out. So, the circles are your cores. Okay. You will see that there is a L1 and L2 cache for every core or every processor. Okay. RAM is going to be shared in a symmetric multiprocessor. Even that is not true in certain types of multiprocessor, but by and large the kinds of machines we deal with, RAM is shared across all processors. Caches are not shared. Caches are specific to a core or a processor. Okay. So, this can raise all kinds of problems, because if you have two processors that are executing, let us say, the same process, multiple threads, okay, they might have similar data loaded in their caches. Okay. If you write to one variable and that same data is actually cached on another processor, that data is now stale. Okay, because you just changed the variable, you just said x equal to 5. Okay, you executed that. So, the value of x has changed. Okay, so, whatever is in your cache will change. You might propagate that to RAM, it is going to change, but if some other processor also cached the value of x, that cached value is now stale. Okay. You can't let that happen, because then if that other thread tries to access x, you are going to get a bad value. Your code is going to have a problem. Okay. So, the hardware actually has to manage consistency of these caches by ensuring that if the same data is cached in multiple places, if it changes in one location, it gets invalidated in other location. All of this is called cache consistency and cache management, as done in hardware, but it actually gets quite complicated depending on what kinds of consistency guarantees you provide on at a hardware level. Okay, that clear? Now, OS does not actually do much here. All of this is done in hardware for you, but you do still have to take care of these issues. Okay. Now, there are two concepts there that I mentioned, which is not really important from a hardware cache perspective, but when we get to things like file systems and so on, where you build your own caches in memory for the process, these things actually become important. Okay. So, whenever you have any cache, okay, when you make a change to some data that is stored in the cache, you have to decide how that change actually gets propagated to wherever the primary copy of the data is stored, which typically is going to be RAM. Okay. And you have two policies you can use. One is called write back and the other is called write through. Okay. I do not know if people have heard of what write back, write through is. Okay. Write through essentially means anytime you change something in the cache, you immediately go and change the primary copy also. Okay. So, your writes propagate all the way through, that is why it is called write through. Okay. Write back simply says when you make a change, you only change it in the cache, and at some later time it gets propagated to the primary copy. Okay. In case of hardware caches, we just play safe and you do write through. Okay, because if you just change things in the cache and some other processor start accessing that value, your code is not going to have a problem. Okay. But when you do other things in the OS like file systems, you get to pick whether you are going to use write back or write through. Okay. So, for example, okay, or your file system is going to actually keep a cache of recently accessed files in memory. The primary copy is on disk. Okay, that is where your files are stored. But when you are accessing a file, that file might be cached in memory. Okay. Let us say a program changed that file. Okay, basically you wrote some text to a file. Okay, now you get to decide whether your file system is write back or write through. You are going to have a system call. The system call is going to change the value in the file. Okay, you could just change the value in RAM and say I am done. Okay. And at some later time, your file system can say I am going to do a flush, I am going to take that data and actually write it to disk. Okay, this makes writes much faster, because writes are simply writing to RAM, not writing to disk, which as I showed you is orders of magnitude slower than memory. Okay. So, as a performance optimization, many file systems will actually use write back caching. So, when you actually write to a file, it does not immediately change on disk, you actually only keep that change in RAM, and at some later point to flush it to disk. Okay. So, this performance optimization comes with a trade off. Okay. Trade off is safety. Okay. So, what does safety mean? Suppose that the power goes out on the desktop. Okay. You have not yet written the stuff out to disk. Okay. When you boot that machine back, you are going to have an old copy of that file. Whatever changes you made which are not flushed to disk will be gone. Okay. If you are willing to take that risk, then you actually get much better performance. So, if you say I cannot take that risk, and every time you actually write to a file, you are going to implement write through, which means all your writes are going to see essentially disk latencies. They will actually run at the speed of disk, not run at the speed of RAM. If you are I/O intensive in any for any reason, maybe you have a database, you are going to essentially slow down performance significantly to get better protection, okay, from things like crashes and failures and things and similar problems. Okay, so it's always a trade-off which one you use. At a hardware level, you essentially do the safe thing, but at a software level, when you do file system and many other things, you actually as an OS designer get to decide whether your caching is going to be write back or write through. Is this clear? Any questions on this? Yes.
We write back, I mean, what's the timing?
Okay, when do you write back? That's a good question. So, it is basically dependent on the operating system. Okay, you might say I do 30 seconds, every 30 seconds I go flush to disk, things of that sort. So, there is no good answer to that question, right. So, it is how frequent. So, the more you keep in memory, the more writes you are going to save, because all the writes are being absorbed by RAM. Okay. But less safe it is, because the chances of something bad happening keeps going up. So, you have to make a decision how long is good enough from a performance standpoint and also is safe enough. So, I think 30 seconds is a number that many OSs use. Why 30? I don't know. Okay, it could have been 10 or 60, but that's what you will see in many cases. Okay. Now, there are other optimizations that OS can do, which is if the disk is idle in the background, it might not even wait 30 seconds saying there is nothing happening, maybe an opportunist write things. When there is some other process running later on, I do not have to go do some writing. So, there are other things you do, but there is a limit for which you basically wait and then you flush. Okay. Any other questions on write back and write through caching? Okay. So, let us talk about the last piece, which are all these other hardware features I talked about. We will start with traps. Okay, we already encountered traps once when I talked about system calls. Okay, I said trap is a way by which a process can invoke the OS and ask it to perform some sensitive operations. Okay. And then what a trap is essentially a software interrupt. I presume you have at least heard of the term interrupt. Okay, yes? Anyone know what an interrupt is? Okay, so traps are essentially software interrupts. Okay, they are conditions that essentially do the same thing as what an interrupt would do. So, for example, you could have divide by 0 fault, that is a trap. You try to access memory that violates the base and limit register, that is a trap. System call, also a trap. So, there are any kind of special conditions which could be errors or which could be legitimate reasons why you invoke that trap to invoke the OS service and things of that sort. Okay. Now, the way you are actually going to implement trap is essentially called a trap vector. It is essentially a table. Okay. It looks like this. Okay. It looks like some hex values. Essentially, all of these values are addresses. Okay. So, every kind of trap you want to support is going to be given a number. Okay. But it is a system call as traps 0. Let us just say that is going to be trap 0. So, what you will put in that table is essentially the memory address of where the code for that system call resides in the OS. Okay. So, if you do file IO, okay, let us say you are doing read or write, you can basically say that is trap 0. I am just making up an example, that is not how actually it will work, but let us say you call that trap 0, you put the address of that trap there. Whenever that trap occurs, you just index it into the trap vector, you look at that memory address, you change the program counter to that memory address. Okay, and then the OS starts executing code that is residing at that address. That is where that function resides. That is your trap handler. Okay, or also in the case of interrupt service routine. Okay. So, this is basically how traps are going to work, where you have a trap vector that is supported by hardware. Okay, you can define what the traps are, what the numbers are, load the address when the OS boots up, and whenever a trap of that kind occurs, you index and you jump to that location. Okay, so, system calls will have a trap. Many of these things that we talked about is essentially going to have a trap. Okay, and then the slide essentially shows you a generic trap handling routine. So, whenever a trap occurs, you have to suspend execution of that process, which means you save all of its registers and whatnot to some memory location. You then start executing the OS, okay, and then you essentially have to flip that kernel mode bit on, okay, and then in the OS is going to index into the trap vector, execute the trap, and then at the end you are done with the trap, you are going to switch back to the process that executed the trap or triggered the trap. Okay. So, the same set of instructions are going to be true for system calls, because system calls are implemented as just another trap as far as this mechanism is concerned. Okay. So, as I said, many kinds of traps. We'll get back to the traps later on. Yes, question. Okay. Do signals trigger a trap? So, signals are also software interrupts. You could implement them using a trap as well, and in some operating systems actually do use traps to implement signals. Simply, signals are also a way by which processes communicate. Okay. And many signals are actually a trap, because if you say terminate a process or you send a kill signal in Unix, that will actually involve you to go to the OS and terminate the process, things of that sort. Okay, we will come to signals at some point when we talk about these things in more detail. Okay, but yes, the short answer is yes. Any other questions? Okay. All right. So, last thing we want to talk about is I/O. Okay, and this is again something we will come back to. This is just what hardware features do we need on a machine to support I/O. Okay, you should know what I/O is. Essentially, anything that you need to communicate with a peripheral requires you to essentially implement it as an I/O routine. Okay, and then the question is, how do you implement I/O and what hardware features do you need to do this? Okay. So, the simplest method to do I/O is what is shown here, first part of that picture, which is labeled synchronous. Okay. So, again I/O is sensitive operation. So, it is going to be implemented as a system. What is going to happen from a hardware perspective is you will basically invoke I/O, okay, then the process is going to be suspended, the OS takes over. In this case, the OS is going to handle this by invoking a device driver, because the I/O requires you to communicate with a device. Okay. So, the part of the OS that is going to handle this is going to be a device driver. So, you go into the OS and then the OS hands that request, whether it is read or write, to the device driver. The device driver is then going to actually know how to communicate with the device. Every device is going to be different, whether it is a USB device, it is a graphics card, it is a disk, they are all different kinds of devices. It is the job of the device driver to know how to communicate with the disk, how to write to a graphics card, how to write to a USB printer or whatever else the device might be. Okay. So, essentially that piece of software which resides in the OS is going to perform that I/O for you, and then you are going to return. But until that point, the process is just blocked. It is not doing anything. That is what synchronous means. Synchronous is a synonym for blocking in this case. So, this is blocking I/O. Okay. The other way to do it, which is shown here, is asynchronous. And as you can imagine, that means non-blocking. Okay. So, the way this is going to work is the OS or the requesting process is essentially going to invoke the I/O instruction, you hand it to the OS, and then the OS is going to return back to the process saying I will take care of it, and then it is going to asynchronously execute that I/O while the process or this process or some other process executes. And once you are done, you are essentially going to raise an interrupt saying that I am done. Okay. That process can do something else, it can block, well, it will not block in this case because it is asynchronous, but it can do something else in the meantime, and at some later point you will be told that your operation completed. Okay. That is asynchronous I/O. Okay. So, one is blocking, the other is non-blocking. Okay. Both of them require some hardware support, it requires device drivers and things of that sort. Okay. And the last type of I/O is what is called memory mapped I/O, and what this essentially allows you to do is take a device and make it look like RAM. Okay. So, reading and writing to RAM is very straightforward. You essentially pick an address and then you either read from that memory address or you write to that memory address. Okay. Very straightforward. Okay. What memory mapped I/O does is it basically takes an device and it gives it a special memory set of memory addresses. Those are not real memory addresses, okay, fake addresses, but those addresses refer to that device. So as far as the process is concerned, it can just read and write to those addresses as if it was reading and writing to RAM. Okay? But what happens internally is when you do that, it actually triggers I/O. So you don't need anything specific to read or write to that device. You're just reading or writing to what looks like RAM, in this case memory. Okay? Your device is mapped to memory. That's why it's called memory mapped. Okay? So every device that uses memory mapped I/O is going to get a specific address range that allows you to do this. Yes.
Is it the same as direct memory access?
Okay, is a good question. So I didn't talk about DMA. I was going to talk about that. So memory mapped I/O is not the same as direct memory access. Memory mapped I/O literally takes a device. So I'm going to draw a picture here. So, okay, so that's RAM. Okay, so now you have disk. Okay, and maybe there's a disk file. So if you want to take that file, you can essentially map it to this part of RAM. So when you are reading or writing to this memory, as if you can read or write to any variable, you can do that, and then that will trigger I/O to that file internally. You don't actually use reads or write to access that file once you map it to memory. So that is memory mapped I/O. Okay. You said what is direct memory access or DMA? That's actually a different way. I think there was a slide here. Let me check. No, there's no slide on DMA. But let me explain what, since the question was asked, what direct memory access is. So what DMA essentially does, excuse me, is it allows you to free up the CPU from doing some mundane I/O tasks. Okay. The most simple way to do I/O is for the processor to take 1 byte of data at a time and read or write to that device using the device driver. Okay, so you take 1 byte, you write it to a device. You take another byte, you write to a device. If the CPU is going to be doing this all the time, it's going to essentially be very wasteful. Okay, because I/O is slow, and it's going to be basically doing a lot of this reading or writing, and it's going to slow things down. Okay. What essentially DMA allows you to do is there is an extra controller which is called the DMA controller. Okay, which allows the processor to the CPU to tell that DMA saying, I want you to do some I/O. Okay, here is a buffer in memory. Okay, so this is your DMA processor or DMA controller, not a processor, it's a controller. So this is your CPU. Okay, so you tell the DMA controller saying, go take this buffer, okay, and then write it out to a device. Okay, and then the CPU can go off and execute some other process. This DMA controller is actually going to go and access that RAM and just take those bytes and do whatever that CPU would have done in the slow, simple I/O scenario. Okay. So you're essentially offloading I/O to another controller and saying, you take care of it, I'm going to execute some other process. Okay. As you can see, DMA is not the same as memory mapped I/O. Memory mapped I/O simply says the device essentially looks like it is a piece of RAM and a process can directly read or write to it. A DMA is a way of doing normal I/O by saying, let's free the CPU and just offload that I/O work to another piece of hardware that will take care of it for us. Okay, yes, question.
So are the first three methods like basically just different ways of abstracting it and from the perspective of the processes? Like I/O is still essentially done the same way in terms of.
Yes, so these are all different ways to do I/O and they need different hardware support, right. So if you want to do DMA, you need a DMA controller on your machine, otherwise you can't do DMA. Right, you will have to essentially just do the standard I/O, which is synchronous or asynchronous, right. But yeah, from a processes perspective, I/O is I/O, right. When you read or write to a file, it doesn't matter to you whether it's done internally, done synchronous, asynchronous, DMA, memory mapped, it's still doing I/O, but these are just very different ways of implementing things, right. So there are different devices for which different kinds of I/O actually make sense, right. If it's a graphics card, okay, memory map might make sense because you are writing an image, you just write it out to what looks like RAM and it shows up on your monitor, rather than writing 1 pixel at a time to the graphics card memory, which looks completely wasteful, right. So that's an example of why certain kinds of I/O peripherals prefer certain kinds of ways of implementing I/O. Okay. Yes.
When you say device in memory mapped I/O, so examples, like is it hard disk or something like that?
Yes. So question is, what is the device? That's an hard disk. That's a device. Graphics card device. Keyboard device. Okay. Mouse device. Anything you plug into a USB port is a device. Printer is a device. Lots of devices on every machine. Right. So a keyboard is a good example where you do want to read 1 byte at a time, because you press a key that generates 1 byte. You just go read what character you typed and you show it on the screen. You're not going to do DMA for a keyboard necessarily, because you're not trying to read lots of characters, because you just type one key at a time, right? So different devices need different kinds of support. Okay. Any other questions? Yes.
Does system using like persistent memory, like using the same model or a different model?
Okay. Well, question is, what about persistent memory? We didn't talk about persistent memory at all. Okay. So far, we are assuming that RAM is volatile, which means you turn off your machine, whatever is in RAM is gone. Disks are persistent, which means you can turn off your machine, turn it back on, your files are still there. Persistent means, does it stay after you power it down? Okay, that's what persistent means. Okay, so our standard operating definition is RAM is not persistent, disks are persistent. Okay. Now, having said that, you asked about persistent memory. Of course, there's this new kind of memory where your RAM will also persist across memory cycles. It's not volatile anymore. Okay. How do you design operating systems of persistent memory is still an ongoing debate. Okay. There are many ways to do it, because once your RAM being persistent, the difference between processes and files are kind of gone, because everything just stays as is, right. So RAM is just faster than disk. So what do you store where? All of that becomes an interesting question. It's not something we are going to necessarily talk about here. Okay, but it is a very interesting problem that many OS researchers are thinking about. Okay, you had a question.
Would you classify DMA as asynchronous I/O, or is it an entirely different method?
Okay, would you say is it asynchronous or not? It is at some level asynchronous, okay, but that doesn't mean it has to be. The process can still be blocked while the DMA is actually, in some sense it's slightly orthogonal, but you can think of it as being asynchronous by and large, because the CPU is offloaded, the CPU will actually get a interrupt from the DMA controller saying it's done. So it works very well with the asynchronous method. Okay. Any other questions? Okay. So we have a little more time and a couple more slides. So I talked about interrupt based asynchronous I/O in some sense already. I'm not going to go through this again. So one thing I did want to mention here is when you do I/O, you essentially want to do it in a way that does not allow you to get interrupted while you're in the middle of I/O, because bad things can happen. Okay. So one of the things you will see in many of these device drivers is you will see that they are actually disabling and enabling interrupts. And at the very beginning, I did mention that that's an hardware feature. Not sure why this is flickering. So you'll see that that's an hardware feature. So what does it mean? Okay, so when you disable interrupts, that means that at that point, anything that could trigger an interrupt, which is timer expires, whether a network packet arrives, none of that is actually going to be handled by the OS anymore. It's just going to ignore them. Okay, so this the interrupt service routine or the I/O device driver can actually run until it is done doing whatever it's doing, and it disables interrupts again. Okay. So this allows enabling and disabling interrupts allows you to run a piece of code without any risk of it actually getting interrupted and something else starting to execute on the machine. Okay. So it is a feature that the hardware provides, but it's also a feature that must be used really carefully. Okay. Once you disable interrupts, if there is a bug in that device driver, okay, and maybe it goes in an infinite loop, your machine is hung, because even the OS cannot take control back, because the device driver will just continue running. You cannot interrupt it, you can't do anything. Okay. So, and what that also means is everything else is going to have to wait until you are done whatever you are doing and you re-enable interrupts. Okay. So this is used for very specific purposes. I/O is one. Synchronization, which we will talk about in just a moment, is another. If you want to do things like locking, Okay, you want to do things atomically, that's another place where you could essentially use disabling of interrupts. Saying I disable interrupts, I do whatever I need to do, so I essentially I have a lock, okay, and then I re-enable interrupt. Okay, that's one way. There's a better way to do locks than using interrupts, but that's still a way to do it. Okay. So you will see that this is used in the OS kernel at very specific places where you want absolute guarantee that nothing else should happen while this code is being executed, because bad race conditions will cause bad things to happen. Okay. So that's a hardware feature to keep in mind. It's used, as you will see in I/O, it's used in some other cases as well. Okay. So timer instruction is another assembly instruction where you can have a timer. Okay, when the timer expires, it triggers an interrupt or a trap. Okay. It's often used for many things like CPU scheduling, where you say, let's run this process, it gets to run for 100 milliseconds. Okay. How do you know 100 milliseconds? When 100 milliseconds have elapsed, you essentially start a timer. When the timer expires, okay, you will essentially jump into the trap handler. In that case, the CPU scheduler will run saying, okay, that process's time has run out, now I will execute some other process. Okay. So that's one way to do a timer. You can of course do timers in your processes as well. If you use timer instructions in application processes, you can say let something run for 5 seconds and then, or you can sleep for 10 seconds. That's also a timer process. Sleep is implemented as a timer instruction. Okay, so there are many uses of this timer instruction, and the hardware actually has to support this for you to implement CPU scheduling, sleeps in processes and things of that sort. Okay. So the last thing I'll mention here is synchronization, and so in this course we are not going to do a lot of synchronization. Okay. You probably have done some of this in an undergrad course when you did threads, concurrency, locks and things of that sort. Okay. But just for sake of completeness, it's worth mentioning that the hardware features you are going to use to implement synchronization are either the enabling and disabling of interrupts, which I just spoke about. So you can implement a lock by essentially using this notion of disabling interrupts, or you can also use another instruction which is called an atomic test and set instruction, okay, which allows you to read a value and modify it in one clock cycles atomically. Typically, reading and changing will be two separate instructions. Okay. And if anything is spread across instructions, you can always have the risk that something else might happen between the execution of those two instructions. There may be an interrupt, for example, and only the first instruction is executed, but not the second one. Okay. So if you want absolute guarantee that both of those operations have to happen together and always together, you need to essentially use a specific hardware instruction to do that, because that's not going to be guaranteed otherwise. Okay. Test and set is one such instruction. Okay. Maybe at some point we'll come back to that and understand how it allows you to implement locks and things of that sort. Okay. All right. So let's see. I think we kind of have only one thing remaining, which is virtual memory and TLB. Okay. So I don't know if you heard the term translational look aside buffer. It's also called TLB. That's the acronym. So it's a special kind of a cache. We talked about caches already. Okay. So TLB is essentially a kind of a cache that keeps a mapping of where pages of memory are stored. Okay. So it allows you to access memory pages very quickly. Okay. And then if the page is not stored in memory, it creates what's called a page fault, in which case you actually have to go to disk and fetch it. Okay. So what TLBs are used for is this notion of virtual memory. Okay. What virtual memory has nothing to do with virtualization or virtual machines. Okay. Just the term virtual is common to them, but they are completely different things. What virtual memory is basically an abstraction you give to a process where you give it the illusion of infinite memory. Okay. Maybe your machine has 16 GB of memory. Okay. What if you want to run a process that's bigger than 16 GB? Okay. If that process has to reside in memory while it's executing, you're out of luck, because you don't even have enough RAM to load the process, let alone run it. Okay. So what you're actually not going to load that entire process in memory. Okay. You are going to keep parts of it on disk. Okay. So you are going to use a disk as a backup for RAM. You are going to have a portion of the disk that essentially stores things that you don't want in RAM and you have temporarily stored it on disk. Okay? Because disk is much bigger than RAM. You might have 1 terabyte disk and you might have only 16 GB of RAM. You can give processes an illusion as if there is no limit on the amount of memory available on that machine. The process size can be larger than RAM, for example, or the total size of all processes is always greater than size of RAM. You can start 100 processes, each of them could take an arbitrary amount of memory. Okay? The sum of their memory sizes will be far greater than the amount of RAM you have. Yet everything just runs as if there is no limit on RAM. Okay? The way you do that is you create this illusion of infinite RAM, which is you are going to essentially use disk as a backup for RAM. So the way you implement virtual memory is you only have subsets of processes stored in RAM at any given time. Okay? That subset is often called the working set. That's the part of the process that you are currently executing. That's the only thing that's stored in RAM. Everything else is stored on disk. Okay? When you start executing something that's not in RAM, you are going to create a condition called a page fault, and you are going to bring those pieces from disk to RAM. Right? Then you can actually take some part of RAM and put it back on disk. So you are going to essentially page things in and out, which allows you to now run processes that are either bigger or in the aggregate they exceed RAM. Okay? So to do all of this efficiently, you need some hardware support. Okay? That is where this TLB is going to come in. It's going to keep all this mapping saying what is in RAM, where is it stored in RAM, and things of that sort. So you can quickly go and access whatever is in RAM. If it's not in RAM, you are going to bring it from disk into RAM and update this mapping saying first page is stored at this location, second page is stored at some other location, and so on. Okay? So we heard the term page table. Okay? Page table is a mapping of pages of that process and locations in memory or disk where they are stored. TLB is essentially a cache for the page table. Okay, so you can essentially do page table access very quickly, because the page table itself is going to be stored in OS memory. Okay. If every memory access requires you to access a page table, which is also stored in RAM, you slow down every memory access by a factor of 2, because first you are going to go to the page table, then you are going to go access that memory. So every assembly instruction is going to run twice as slow because it requires 2 memory access. You don't want that to happen. Okay? So you are going to keep parts of the page table in TLB, which is a fast cache. Okay? So you are basically going to run at speed, normal speed. It's not going to look like, because parts of your processes are not in disk, you are using page tables, everything is going to run slow and things of that sort. Okay, so you have these hardware caches that are going to allow you to do interesting memory optimizations, like having virtual memory and not limiting processes to whatever you have in RAM and so on, yet not slowing things down. Okay, so that's what you are going to use it for. Questions? We'll get to TLBs when we get to virtual memory somewhere later on in this course.
What's the relationship between the memory I/O and virtual memory? Are they totally different?
Oh, you mean to say memory mapped I/O?
Yes.
Okay. What's the relationship between memory mapped I/O and virtual memory? Okay, memory mapped I/O is essentially just a way to take any device and make it look like it's part of RAM. So rather than using explicit instructions, you just read or write to RAM that triggers read or write to that device. Okay. Virtual memory has nothing to do with memory mapped I/O. It's not I/O. This is just a way of essentially having the ability to run processes that either exceed the size of RAM or lots of processes where you couldn't all fit them in RAM. You just essentially use a disk to store everything and only keep parts of it that you are executing currently in RAM. Okay, so two different things. Anything else? Okay, so we'll end it here for today, and then next time we'll start our real topic, which is going to be microkernels. Just 1 second.